You know that Gilbert and Sullivan song?
No, I didn't.
A wandering minstrel,
Oh, right,
thing
yeah.
of rags and patches, of ballads, songs, and snatches, of dreamy lullabies.
Right.
Well, Marilyn, looks as though I scared him away.
Oh, no, we got another 5 minutes. People don't usually come till it's time to come. Or a little later.
No, they always come 10 minutes after it's time.
Yeah, that's called Kaslo time.
Kootenai time.
Kootenai time, okay. A little more general.
15 minutes and still can't tell.
Yeah, oh, I see.
Don't sit so far away.
I see.
This is
Change.
Has anybody come in yet that wasn't here yesterday? Okay, great. I'd like to have you all sign the book. Actually, maybe I should have everybody sign the book. And we're just asking for donations. We're not asking for a specific fee. So where's Eric's hat?
It's in the car.
I
Okay.
don't want to keep anybody out of this information just because they don't have any money.
So maybe anybody that wants to donate can just put it in Eric's hat.
Invest in this. I heard once they
Yeah, I'll wait and just send it around and look at everybody again. That might be an idea.
some aspect of modern telescopes. Because
Got him.
Pretty close. I don't know if I got him, but
some
I...
call it Dobsonian
Oh, great,
telescope.
okay.
Yeah, there's
I
something
must
called a
have-
Dobsonian telescope. So I'll tell you a story. I was in Boston, and there was a lady from South America who was in charge of feeding me and sleeping me. And in her inimitable South American accent, she said, "I don't know much about astronomy, but I read in the magazine there are these different kinds of telescopes. They're Newtonian telescopes, and they're Dobsonian telescopes. I thought Dobson died a long time ago."
Oh, there he is.
But she didn't think it was funny, you see, when she said it. But she was in the audience when I told the story. Then she saw how funny it was.
Can I have everybody's attention? There's still a lot of people that said they were going to come, but they might be here a little bit late. I have two things to announce. First of all, I'd like to have everybody sign up again, or sign so we know who's here. If you wouldn't mind putting your name and your the location, whether you're from Kaslo or somewhere else, and your phone number, I'd appreciate it, so we can kind of count heads afterwards. And John normally gets a lot of money for these lectures, but he's doing it here
That
for just
depends on where I am.
for just donations. In centers like this, he does it for just donations. So Eric's got a hat, and we're just gonna send it around. So if anybody would like to donate to his expenses.
And you can put your play money in there, and we'll take it. I'll see if I get it translated in the States.
You'll convert it to funny money. Okay, so I'm going to send the book around first, if that's okay. And if you wouldn't mind just putting down who you are, so I'll know how many people were here tonight and where they all were from.
Now, usually I scare the people away after the things that we're going to do tonight. Not usually after the things we did yesterday.
I can.
So there might still be some more people coming. Usually people quit this class just when we get to the interesting stuff. I'm not perfectly sure why, but that's how it happens so many times. We talk about these stupid things, like that's made out of hydrogen falling together by gravity and makes into galaxies and stars, and stuff like that, and then they flee. Is it time for us to start yet?
Well, it is, but there's still a lot of people not here, but go ahead. I know, knowing Kaslo, there will be a lot of people come in, but we can't wait too long, so go ahead.
Okay, you people can ask me questions first. You remember we have some homework. How did the stuff in the solar system get sorted so that the planets in the sun could be made out of hydrogen, iron and rock, and the planets farther out could be made out of hydrogen and heat. So that's your homework, and I'm going to show you some slides. Are you still running that fan?
Just a fan.
Oh, no, don't run the fan.
Part of
It's already cold. We're in Kaslo. Anyway, do you need to ask me some questions first? Oh, come on, there has to be some questions.
Yeah, I'll have a question where we left off last night.
All right,
I asked
well-
the question how thing could escape against the gravity, and you explained why it did. But isn't there a center white star left?
A center where?
Little white star left in the center after the
Oh,
explosion.
after it, oh yes, it's a neutron star.
Okay.
Oh, sure.
So my question then is, how can that one resist the explosion?
Oh, well, that's the one that caused the explosion. That's not the one that was blown away by the explosion. The center collapses like this, and the energy that's released by the collapse of that neutron star, the energy that's released by the collapse of the neutron star, blows the other stuff away. It doesn't blow itself away. Then all the energy would be gone again. It's the collapse of that in that awful gravitational field that causes that thing causes the outsides to blow away. One of those neutron stars, they figured that if there was a mountain on it 1/2 an inch high, it would take several generations to climb it if all of the energy of those several generations was devoted to climbing that 1/2 inch mountain. So it's not so easy to get something off of a neutron star. If we wanted to get a marshmallow off of a neutron star, fortunately the surface material on a neutron star is 1 billion times as strong as our best steels. 10 to the 18th times as strong as our best steel. So we make a little cavity here with a little bunghole at the top to put our marshmallow in. And inside we've got an atomic bomb. And we have it arranged so that all of the energy of the atomic bomb explosion goes into our marshmallow. And when we blow it up, and the thing around it is so strong that we don't have to worry about that. So then we blow up our atomic bomb, and all the energy goes into the marshmallow, and it just lifts off. That's why this stuff doesn't go away. The other stuff is blown away by the energy that was released by this collapse. That's all. Yeah.
Would you repeat yesterday what you said about how much stuff the mouse?
Oh, the amount,
Yeah.
how much stuff there is in the universe?
Yeah, I think
The density of the universe? About 20 drops of water to 1 billion cubic miles.
And what was it you said about the mouse?
What?
You said,
Well, a mouse isn't heavier than 20 drops of water. A little heavier than 20 drops of water, yeah.
oh, okay. Thank you.
But we're within the ballpark.
Yeah.
It's more than enough to make a swallowtail butterfly. You can drown a swallowtail butterfly in 20 drops of water. Any more questions?
How did we get so concentrated?
What?
How did we get so concentrated?
By
We're very
meditating.
concentrated.
I don't know what you mean by that.
Well, there's so much space and so much universe and
Oh,
everything.
and
How did we get so
Well,
concentrated?
the stuff fell together and made into a galaxy, and the stuff in the galaxy cloud fell together and made into stars. And the stars have planets, like our sun had some planets, and we're made out of all this stuff that the blown up stars threw away. And that's how we got like this.
And so, and the iron is stronger in the center, and outside are the more gaseous materials, right, of this solar system. And that's where we're at now, no?
The sun isn't made out of iron.
Where did the iron come from? The closer planets? Or?
No. Came from the stars out of which the solar system was made. Remember, we're a disk star. Remember the stellar winds of all those stars blew away all the dust from the exploded stars out of the hovering layer, and the dust from the exploded stars flattened into the disk. Remember how we drew it on the board? The dust from the exploded stars flattened into the disk. So the disk stars are dusty. And our sun is a disk star. It's about 2% dusty. So when it condensed out of that big cloud of hydrogen, mostly hydrogen with some helium and a little bit of dust, the planets are made out of the dust.
And the dust is broken up into different elements. It has different elemental
Well,
elements.
it's no fair saying that it's broken up into different elements. It's made out of the various elements. Now, the astronomers are a really strange lot, you know. They call everything after helium metal. We're talking about metal-rich stars. That means for them, anything beyond helium is metal, okay? Like oxygen and water, they're all metal for them. But that's just their language. They're called metal-rich stars. So the stuff in the solar system, the original cloud probably had 2% dust in it, and 98% hydrogen and helium. And you have to tell me before the evening is out how this stuff got sorted so that the planets near the sun can be made out of iron and rock. See, you're really asking me what I've already asked you.
Yeah, I know.
Just trying to cheat. But it'll get you nowhere.
I just trying to figure it out.
What else? All right, it's not dark enough to show slides, is it?
We can turn the lights out.
All right, you can try that.
Okay.
Okay, you can try to fire it, or I can fire it. All right. Now, I'm supposed to have 3 pictures of clusters of galaxies. But the difficulty is that I travel all over the continent, as down as Mexico and as far up as Canada, and one of these pictures at a time falls into somebody's projector and stays there. And the last picture of galaxies is in New Hampshire. So all I have left now is the computer-generated pictures of galaxies passing in the night. If galaxies pass at all, they pass at night. Now you have to watch what happens. What you need to notice is the tidal effects. I'll run it fast first. This is not in real time. It would take longer than that. Now let me see if I can do it slowly. Now what happens is that when they get close to each other, they reach out toward each other. But these are spinning a little bit, see? So that's why that one's got its bows, not toward the big one, but somewhere else. See that? Because this was done for spinning galaxies, I think, already. A little spin they had in them. But you see, the close sides get pulled too hard toward each other, and the hind ends lag behind. Do you see it? The hind end lags behind. And by gum, you get 2 spiral arms, one on the front reaching out for the little galaxy, and one on the left behind. Don't you see? Now we have real live galaxies playing contact sports, just in case you thought I was kidding you. Let's see, where do we focus this thing?
Here, I can focus that.
This thing focuses faster than that. So these are galaxies playing contact sports. Now, when galaxies pass each other like this, some of the stars from here will end up in here, and some of the stars from here will end up in here, and some of them will be thrown out completely. When you cut the butter with the butter knife, some of the butter gets on the butter knife, and some of the butter knife gets on the butter, and some of the butter escapes completely and gets on your toast. So that's what's happening here. Oh, by the way, did you see that? That slide's been almost melted, see it? Coming up from the bottom? That's what these projectors do to it. So here we have some more galaxies playing contact sports. Galaxies are very spacey, and they do indulge in contact sports. Stars, on the other hand, are very lonely and then goes permanently in non-contact sports. Now, this is a cloud of hydrogen in our winter Milky Way, making into a cluster of stars. And you see the stellar winds of these stars have blown a hole in it. I want you to imagine that it's a much larger cloud, big enough to form a whole galaxy. Can you show us one more and then back up one? Now you see, this is a cluster of stars. There's 500,000 stars in a bunch. Now I can back up again. And what you have to imagine is that in the center of the galaxies, hundreds or maybe even thousands of clusters like that would form in the air. And the stellar winds of all those stars would blow a hole in the air. Meanwhile, all these little bright patches you see would form into clusters like that, then fall into the center and coast on through, and then fall into the center and coast on through. Got it? Got it or not got it?
Got it.
All right. Then what happens is that the stellar winds of all those stars blow most of the hydrogen away. Most of the hydrogen helium gets blown away by the stars out to a hovering layer out here. All right, you can shoot two more. So these are old stars actually. This is 500,000 stars, and these are old stars, about 17 billion years old. These are made of nice clean hydrogen and helium before there was any dust to make stars out of. Go on. Now this is a galaxy which we sidewalk astronomers call Bernice's hairpin, because it's right near a cluster of stars called Bernice's hair. Coma, Bernice's. Coma does not mean comb, it means hair. And so what happens is our hovering layer flattens into the disk from both sides, you see, and with it goes the dust of the exploded stars. And so in this disk, all the stars like our sun are born. And the original stars, they're on what I call pincushion orbits. They fall into the center and coast on through, and then fall back and coast on through. But these are going round and round like the rest of us, okay? Round and round. So I want to know, what are the differences between the central bulb stars and the stars of the disk?
Size?
All right, which ones are bigger? Never mind, I can't answer, I don't know.
In the center.
Right?
Center ones are bigger.
No, we don't know that.
The outside ones have dust.
What?
The outside one, the ones in the disk have dust.
The ones in the disk have dust. That's one difference, is a difference in composition. The disk stars have dust and the others do not. Go on.
The outside ones are younger?
Yeah, the disk stars are younger. The disk stars are younger. Go on, what else? Come on, what else?
Well, the center stars have daylight all day.
No, none of them have daylight. Daylight is only on a planet like the Earth that has an atmosphere and happens to be near enough to a sun. That's all. The universe has no such thing as daylight.
But could there not be a sun there?
What?
Could there not be a sun in that galaxy?
There are about 100 billion suns in there.
So could there not be
Something like
there?
100 billion.
Could there not be an Earth sort of?
An Earth in there? No. Can't have an Earth in there. You can have planets like the Earth out here because we're made out of dust, and you cannot have any planets like the Earth in there. There's nobody at home in there. Nobody home in there.
Is it because of the density of the center, or?
No, the stars in the disk are all going round and round. These are all on pincushion orbits. These are all going round and round. Those are older, these are younger. Those are clean and these are dusty. Now there's one other thing that's just as important as those, and one of the classes mentioned it, and I cannot come up with it anymore. I'm sorry. There's another very important difference between the central bulb stars and the disk stars, which one of the classes came up with, and I cannot recall it. Okay, fire away. These are the officers of our local galaxy club. This is called the Andromeda Galaxy, and she has two secretaries, a small, bright secretary and a plumper, not so bright secretary. And all over this picture are the stars of our own galaxy with the vice president. Got it? These stars are right next to our eyes. It's like looking through raindrops on your windshield. These are like the raindrops on your windshield when you're looking through your windshield in a distant rainstorm. These galaxies are 2.5 million light years away. Light goes 7.5 times around the Earth in 1 second, and it comes from those galaxies in 2.5 million years. Now, years ago, when we thought that was 2 million light years away, I had a little boy in Sacramento looking through one of my telescopes at this galaxy, and I told him that if you had a spaceship, it could blast off now and reach the moon now. 1 1/3 seconds later, you could get out there in 2 million years. Guess what he said? Too many sandwiches. Okay. Right. Now these are clouds of dusty hydrogen making into new stars in the disk of our Milky Way. Go ahead. This one, through the telescope, looks like a buck duck going over the falls with a black pillow under her neck. You don't see in this picture very much that this is darker than the rest, but it is in the real world. And you see trailing clouds of glory she goes, you see. Now, when you see these pictures here, you see those things as red. When you look through the telescope, you will not see this duck as red. You will see her as white, because these colors are so dim that they do not affect the color cells in your eyes. We have 2 kinds of cells in our eyes, what I call ladybird beetle cells, which are very clever about the details of the ladybird beetle when you have her in the palm of your hand. And then the rod cells, which we use at night. After the sun goes, a little while after the sun goes down, your ladybird beetle cells go to sleep. And then you're stuck with seeing things with the other part of your eye, which is very stupid, okay? In the daytime, with your ladybird beetle cells, you can see the leaves on the trees from across the street. And at night, you can still see the trees. So that's the difference, you see. So these you see with your stupid rod cells, because these never shine brightly. And so these you see that way, and you don't see the colors. Go ahead. Now this one is called the North American Nebula for obvious reasons, and you have to answer my question. How come there's so few stars in the Gulf of Mexico and so many stars in Canada?
Trade embargo?
Come on, why?
Mexico is near the center of it?
Why?
The Gulf of Mexico is more near the center of it?
Uh-uh.
That's a spiral arm.
This is just part of our galaxy.
You're looking at water when you look at the Gulf of Mexico.
No.
No?
This is a dust cloud in front of the hydrogen cloud. So here we can see only the stars between us and the dust. And up there we can look right through the cloud into the background stars of the Milky Way. Got it?
No.
Down here, this is a dust cloud in front of the gas cloud. This is a big hydrogen cloud that goes way over to here. The Pelican Nebula is over here. This is the beak of the Pelican. Didn't you ever wonder where those things go in the Devil's Triangle? The Pelican gets them. No wonder they can't find them. Well, anyway, this is really a cloud that goes clear over to here, but the picture is taken by people who are piggishly North American, just piggishly North American, and so they leave this part out. This part's part of the same cloud, but there's a dust cloud in front. Okay, fire away. What are they?
Meteorites.
No, they're not meteorites. Stars. What stars?
Orion.
Orion stars. Was this picture taken north of the equator or south? North of the equator. If it had been taken south, what way would they be going? This way. And if it was taken on the equator, what way would they be going?
Straight in.
Straight up. This is east. Yes. Straight up.
I realize that.
Now the interesting thing is that if you just take a picture like this and print it up, you can tell how far from the equator you are. Isn't that lovely? You can tell how far from the equator you are just by taking a picture like this. Okay, go ahead. Now, this is of course the Horsehead Nebula, and this one we call the fallopian tubes. This is one of the belt stars, but this is the interesting thing in this picture. There are no stars being born in here, but there are lots of stars being born in here. And the infrared satellite sees this part as bright and these parts as dark. And it sees dust disks around stars in here. This is, I think, the first time we had pictures of numbers of stars with dust disks around them forming planets. And the astronomers think that the stars in here that do not show dust disks around them now have already formed the planets from their disks. Now it'll be a long time before anything interesting happens over here. So let's zoom in one more. We have one on, closer one on this. Now you see, can you see that this stuff is piling up on the outside of this? Can you see that? Now that really is like that. And the reason for that is that this stuff out here stays hot because the ultraviolet light from the stars knocks the electrons off the atoms, and when they come back on, they only give back a little bit of the energy they got being knocked off, so they stay warm. Here it can stay cool because the dust can radiate in the infrared. Hydrogen can't radiate in the infrared. So this can't cool off like this can. This can cool off by radiating in the infrared, and so this one bumps into that and transfers its heat, and then you can get rid of it. So these clouds, in the disk of the galaxy, we have clusters of stars that are much smaller. Remember I showed you a cluster of stars a while back? 500,000 stars in a bunch? Well, these are much smaller clusters. A few hundred stars in a bunch, sometimes even 1,000, but much smaller clusters. Because in the disk like this, the dust makes it possible for smaller clouds to cool off faster. If it's too big, it's too far to the edge to get away to the information. If it's smaller, you've got more surface in proportion to the volume, so they can cool off faster. That's why in the disk, the clusters of stars are smaller than the old clusters that were formed before there was any disk. Go ahead. This is the great nebula in Orion. Everything you see in this picture is the middle star in Orion's dagger. Everything you see here is the middle star in Orion's dagger. Now, they take these pictures with long exposures to show you the bat wings out here, but it spoils all this. So we'll have another picture of just this part. That's much better. Now this green is oxygen. When the electrons are knocked off of hydrogen and they come back on, hydrogen glows in the red. That's the color you've been seeing so much. But when they come back on oxygen, the oxygen glows in the green. So this is the oxygen. And there are new stars in here with dust disks, which the Hubble telescope can see. But that's more recent. Go ahead. This is the Tarantula Nebula in the Large Magellanic Cloud. That's one of our neighbor galaxies. And this is so big that if it were where the Orion Nebula is, which is 1,600 light years away, 1,600 years it takes the light to get to us, this one is so big that if it were where that one is, it would be this wide to your bare eyes in the night sky. You don't have to have any binoculars or anything to see the bloody thing. There's enough stuff in here to make 1,000,000 suns. Anyway, this is called the Tarantula Nebula. Now I have to warn you, these pictures are stupid, okay? And what I mean is, if you look through a telescope at this, the spider's eyes are alive, okay? Because there are stars in here, and you can't see them in this dumb picture. Look, these things don't shine. They don't shine. This is just a bright spot on a wall. When you look through the telescope, the stars are alive, and they shine. So then it looks like a spider. Go Go ahead. These are the Pleiades. What are they called in Japanese? Subaru. Subaru is the Japanese for the Pleiades. They're called the Seven Sisters, and as I said, I didn't name them. But there are about 150 of them. And these are baby stars still in the delivery room. And these blue patches are their Huggies. These stars were born when the dinosaurs died, 65 million years ago. But they're still in the delivery room.
What's that blue stuff?
What?
What is that blue stuff?
That's dust.
That's
Remember the three ingredients in the universe. It's hydrogen and helium and the dust of exploded stars. But in these pictures you see the dust shines blue by reflected starlight, like our sky is blue, remember? The sun lights our sky up as blue. So these stars light this stuff up as blue. The hydrogen knocks the electrons off and they come back on and they shine in the red, and the oxygen shines in the green, but this is just dust. Huggy dust. Go ahead. This is our sun, and our sun is a teeny bopper. And it has magneto-hydrodynamic zits. Now you see the distance between this one and this one? That's almost as far as from here to the moon. That's almost as far as from here to the moon. There's room inside the sun for the moon to orbit the Earth, with 250,000 miles left to spare outside of the moon's orbit. And the sun has a density of very thick maple syrup. I know you heard that it's a ball of hydrogen and helium, and you thought if you just didn't have a string on it, it would just go away somewhere. Well, stuff it. It's worse than a water balloon. And it's very large. There's room inside the sun for 1,300,000 Earths. And it has a density of maple syrup. Go ahead. This is a picture of the shady side of the moon. Can you see that all right? This is a picture of the shady side of the moon. So where's the sun?
behind it.
On the other side, yes, behind it, as seen by us, behind it. Now, this blue that you see around here, that's the sun's corona. The ultraviolet light knocks the electrons off the hydrogen atoms, and when it comes back on, they can only give part of it away, and they keep picking it up in the ultraviolet, giving away a little bit of change in the red, and they get way too hot. So the corona is way up about 2 million degrees, and this is hydrogen with the electrons coming back on the atoms. These are what we call prominences, but this blue is the sun's corona. Now, the astronauts said that when they're orbiting the moon on the shady side, the only way they can tell where the moon is that there's a section of the sky with no stars. When the sun goes down over the mountains on Earth, you can still find your campsite. When the sun goes down over the mountains on the moon, all you can see is stars. Yes?
Isn't it a crazy coincidence that the moon just fits over the sun like that?
Well, it's not going to do it very long, so cheer up. We'll get to that. Yes, it's a coincidence. Now the next picture should be colored like this. Memorize these colors. Go ahead, let's see the next one. This one should be colored the same way. These should be red and this should be blue. Got it?
Got it.
All right. Now there's one thing you have to remember about the sun. The sun is retarded. It never saw a shadow. Isn't that too bad? Everywhere the sun looks, everything is bright, and it never gets to see your shadow. Okay, go ahead. Now this is an old star. See, that star's blue. Do you see it? These aren't blue. That one's blue. That one's 7 times hotter than the sun. And you see the green in here? This is oxygen coming off of this dwarf star. This is the last puff of hydrogen. You remember yesterday we talked about all these things? how the star swells up to a great red balloon and then the outside puffs away, especially around the equator where it's spinning like this, where it goes out too far, then you have the whole atoms forming and they dump extra energy in the cloud and it just puffs away. You see, this is not really a sphere. This comes off in the equatorial regions mostly. And this, we have another picture of another puff way out here and another puff way out here. If you take very long photographs, very, very long photographs, you can see two previous puffs. We think at least 50 puffs have gone off before. This is only a tenth of the stuff that we have in the sun. And we think already 5 times as much stuff as we have in the sun has gone away in these puffs.
What's the yellow?
I don't know what the yellow is. That's okay.
Is that a pulsar or?
No, that's not a pulsar. It's a blue dwarf. It's a blue dwarf. Go ahead. Now this is the same sort of thing, but this one we see from the equator. See, this is the equator around this way, and the pole would be through this way. If we could see it through this way, we'd see the star in the middle, we'd see the green in the middle, we'd see the red around the edge. Can you see that? The red's all wrapped around that way. Anyway, this is named for a famous astronomer. This is called the Dumbbell Nebula. Go ahead. I heard that from a famous astronomer. Now this is an exploded star, that is to say a collapsed star. This star here is a neutron star, and it spins around 30 times in 1 second. It's about 10 or 12 miles in diameter and spins around 30 times in 1 second, and gravity does not allow it to fly apart. You have to think what it would look like if you tried to spin a rubber tire that size around that fast. It would all fly apart. There's no way to hold it together. Or even if you had a steel ring, you couldn't hold it together at that speed. Now there's one of these neutron stars which is spinning around 642 times in a second, and gravity keeps it in at the belly. But the astronomers figure if that one spins up a little faster, it will fly apart anyway. 642 times in a second the bloody thing goes around, and it's 10 and 12 miles in diameter. Must look like a cookie. Anyway, this is the one that collapsed on the 4th of July, 1054 AD, on the 4th of July. On the night of the 4th of July, the Chinese astronomers saw this thing, and they wrote in Chinese, I've seen it in Chinese, they said there's a guest star in the constellation Taurus. If you get your telescope, some of you are making telescopes, you know Taurus is a face of a bull, you know, it's a V-shaped thing like this. Well, I'll do it this way. It's a V-shaped face of the bull, you see, but it's a Texas longhorn, and the horn stars are way out here. Here's the face, the Hyades, and way out here are the horn stars, the Texas longhorn. And if you get your telescope on the dim horn star and move one eyepiece field toward the brighter horn star, you'll be on this cloud. So this was seen by the American Indians on the 5th. You can just give us another one. It was seen by the American Indians on the morning of the 5th of July, just below the crescent moon at sunup. And they drew this thing on the rocks. You see, the chip off, this is all manganese and iron, which has been exposed by the sunlight and all. And then they chip that all off and make these pictures, and they're showing us that the star is about as bright as the moon. The moon is close enough so that the light gets here in 1 1/3 seconds. And this, it takes 6,000 years. Got it? 1 1/3 seconds to get the light from the moon, and 6,000 years to get it from this star. Now the Chinese gave such a nice description of how the light got dim that from their description we can calculate the half-life of californium-254, because in this explosion a lot of the neutrons are dumped into iron and pushed up into californium-254, and has a half-life of something like 50 days, and the Chinese measured it 900 years before we discovered such a thing. Now the Chinese could see this star in the daytime with the sun up for more than 3 weeks. It's 6,000 light years away. They could see it in the daytime with the sun up for more than 3 weeks, and for 600 nights they could see it at night. and then after that they couldn't see it. But it takes a 36-inch telescope now to show it to you. It's still about 100,000 times as bright as the sun. It's still about 100,000 times as bright as the sun, and it takes a 36-inch to show it to you. Go ahead. Now this is the same sort of thing, but this one happened over here. The star that collapsed was over here someplace, and it was 15,000 years ago. So this is the stuff that was blown away from that star 15,000 years ago, and this is the kind of stuff out of which the Earth is made. This is the kind of stuff out of which our bodies are made. We are all recycled supernova explosions. Now, if you give this cloud another 10 billion years, it will go to school and chew gum and listen to programs like this. Now, years ago, I was watching Sesame Street, and Big Bird shows a picture of an egg. She says, "This is a picture of me when I was small." So this is a picture of somebody when he was small. Go ahead. This is Saturn, and I don't have to talk so hard anymore. This is from the ground, and the next one is not from the ground. Now, can you see that it's wider this way than it is this way? Can you see it? Why is it wider that way?
Spinning?
It spins too fast. It spins too fast. And the ring, you see, is an orbiting snowstorm. And I threw some flyers out last night. If you used the paper of the flyers and made a model of Saturn's rings as big as the city of Los Angeles, the paper would be too thick for your model. Shall I say that again?
Yep.
If you made a model of these rings out of paper as big as the city of Los Angeles, the paper would be too thick to represent the rings. The thickness of the rings is something like twice the height of this building, and they're hundreds of thousands of miles wide. Go ahead. Oh, no, don't go ahead. Don't go ahead. I have to tell you the most famous, I think it's the most famous planetarium joke. In the planetarium, they tell you that Saturn is lighter than water, so that if you had a bathtub big enough to float Saturn, it would float, but it would leave a ring. But you see, they leave out all the interesting things. If you had a bathtub full of water that big, in whose gravitational field would you float it? Not only that, but if you had a bathtub full of water big enough to float Saturn, the bathtub full of water would be a star. They leave out all this interesting stuff. They just want to be funny. Go ahead. Now these things don't belong here. These black things don't belong here. See, this is straight up over that one, this one down here straight below that one, and these are straight across, and these are straight across. See that? They're put in by NASA. They're called fiducial marks. They want to know which way they're shooting. They're not there. Okay, go ahead. This is one of Saturn's moons. It got pretty badly knocked, but not broken up. Now the next one is one of Uranus's moons, Miranda, which we think did get broken up. We think maybe even more than once it got broken up and reconvened by gravity, but the pieces don't fit. Wait till the geologists get there with their rock hammers. Okay, go ahead. This is Titan. This is Saturn's big moon, and the smog on it is very much like the smog over Los Angeles. This really does have smog. Anyway, we think that there are lakes underneath that atmosphere. This is the only moon in the solar system with a conspicuous atmosphere. And there's some talk, you know, that there might be somebody out there to talk to. But at any rate, it's pretty bloody cold out there. The sunlight out there is only 1% as bright as it is here, and no one would sunbathe. What else do I have to tell you? I have to tell you that there are 6 big moons in the solar system. Saturn has this one, Jupiter has 4, and we have 1 by accident. This close to the sun, we have no business to have a moon like ours. Go ahead. This is Jupiter shoot again with a great red spot. If you had a blankie big enough to cover the great red spot, you could wrap the whole Earth up in your blankie. Okay, go ahead. This is the home planet of the Martians. And these are the right colors. It's blue-gray against orange. But all through my youth, these patches were shown to be green. That's because the telescopes were so retarded, they couldn't separate the colors. And if you scatter a little bit of orange across the blue-gray, you get olive drab. It's a very simple thing. Now, all the pictures I saw of Mars in my youth had this green on them. And Lowell had this big retarded telescope, and he thought they were green. And Lowell did not know that you cannot have water on Mars. You cannot have liquid water on Mars because the boiling point of water on Mars is colder than the freezing point. Shall I say that again? On Mars and on the Moon, the boiling point of water is colder than the freezing point. So if I opened a tumbler of water on Mars, it would boil until it froze, and then the ice would slowly evaporate like dry ice does here. You're accustomed to that with dry ice. The boiling point is colder than the freezing point. You're already used to it. But it would be the same with water up here. Anyway, go ahead. These are the home planet of the Martians. And you see, there really are straight line detail. There's a whole flock of straight line detail. Schiaparelli was not nuts when he saw those things which he called channels. Canali really means channels. It does not mean canals. Lowell took it to mean canals, and he thought that the Martians were directing the water from the pole caps down to the fields from north and south. But there's no such thing going on Mars. Now, there are craters all over Mars, but there are also these other things. Now, you see all these little black spots? Remember what they are? Fiducial marks. They're not there at all. Go ahead. See, we're all over this thing. We have those stupid things. Now, these are sand dunes on Mars. If they'd ever had dune buggies, they would do it here. Go ahead. This is a dried lake on Mars. We're quite sure that it used to have water, but it cannot have water now. Go ahead. This is the shadow of Mars's bigger moon. It looks like a worm-eaten potato, and I used to have a picture of it in my slideshow, but somebody broke into my van a long time ago and stole all my slides and a snowsuit and a borrowed projector and all this stuff, 2,000 bucks worth of stuff he stole. And he probably threw all the slides away. Probably sold the tray for maybe a dime. You know, if he wants drugs, why didn't he just ask me? Anyway, this moon is the right size, so you could pitch a baseball, and in 2 hours it would orbit. So you've got 2 hours to go in and have dinner, and take your shower, have no liquid water, remember. You have to take a sponge bath, okay? And it's going to be very cold on your wash rag. Anyway, and then 2 hours later, you come out and catch the ball. If you miss, you've got another 2 hours. Okay, go ahead. Now this is the Grand Canyon on Mars. It's big enough to reach all the way across Australia or all the way across the North American continent from east to west. And the Grand Canyon of the Colorado River would fit in this little gully. If you want grand scenery, get out of Canada. Go ahead. This is the big volcano on Mars. It's big enough to cover the state of Oregon. And it's nearly 3 times as tall as Mount Everest. And the lava pit is bigger than San Francisco Bay with all the surrounding towns thrown in. We have another picture of it. Look, you can put San Francisco Bay and all the surrounding towns in there. And this is nearly 3 times as tall as Mount Everest. You know, we can't have mountains that tall here. Do you know why? Because they're the rocks would get squashed. But Mars is smaller than we are, and it has a smaller gravitational field, and you can have mountains 3 times as tall as Mount Everest without getting the rocks crushed. They would slump if it was on Earth. Go ahead. Now this is the home planet of the Earthlings. So that was a volcano we just showed you. So go ahead, we're going to show you a volcano on Earth. This is a volcano in the Mediterranean Sea. This is the Mediterranean Sea out there. And you see this piece of land, and that little piece of land up there, and that piece way over there. And this is a big caldera, like Crater Lake. And this is like Wizard Island, the new volcano coming up inside of the lake. But this is filled with the Mediterranean Sea. Now this was a very big explosion. The explosion that blew Crater Lake blew 35 cubic miles of rock to powder and put them in the stratosphere at 80,000 feet. That was 42-pound explosion. They think this was quite a bit more than that, at least 50-pound explosion here, they think. And Jacques Cousteau does a 2-hour odyssey on this thing. You should see it if you can. He's got a 2-hour odyssey on this thing. There's a whole fleet of ships sunk out there, all covered with great big boulders the size of cars all over the decks. These are loaded ships. This is not that they sank them deliberately. They were sunk by the explosion of this mountain. So the whole mountain blew up like that. And then the Mediterranean Sea came and filled the caldera.
What year was the explosion?
This is a little bit, maybe 10 years after 1500 BC. It's sometime around 1500 BC, and I'm not even sure which side of 1500 BC it is, but I think it's on this side. But you have to think what it would be like if you were a Minoan. In those days, the Minoans, who lived on Crete, ruled the Mediterranean Sea. They took taxes from the Mycenaean Greeks. But after this explosion, the Minoans were gone, and the Greeks no longer paid taxes to the Minoans. So you have to think what it would be like if you were a Minoan on Crete, 5 miles up from the beach. This explosion would be 75 miles away from you, north. 75 miles north of you, you'd see this tremendous explosion. And while you're there in shock, the next thing you'd notice is that you would be thrown down on your face by the earthquake waves that come this way through the rocks. They get to you first, smash your buildings with a thunderous roar, and throw you down on your face. Before you even have a chance to get up, you'll be thrown down on your side by the earthquake waves that come this way through the rocks and take a tiny bit longer, smash your buildings with a second thunderous roar before the first one is quiet, and throw you on your side. This time you have a chance to get up, and you're thrown down on your back by the shock wave in the air that makes you deaf and tears the leaves off the trees. This time you're not sure that you should try to get up. So you sit there in the grass, and the next thing you notice is that you can no longer see where the mountain exploded, because your new horizon is the crest of an ocean wave about to wash you over to the other side of Crete. The Valley of Corpses is on the other side of Crete. The Valley of Corpses is on the other side of Crete. Okay, go ahead. We have one more picture of the volcano, and then a picture of the town on Crete. Go ahead. This is the only town that was ever rebuilt on Crete, but it was not rebuilt by the Minoans. They were gone. It was rebuilt by the Mycenaean Greeks. If you look in the history books, it's the Minoans until about 1500 BC, and then it's the Mycenaean Greeks. Go ahead. This is Venus by ultraviolet light. Don't go to Venus. If NASA sends you an embossed invitation, send it back unopened. It rains sulfuric acid, and the ground is hot enough to melt solder. And the atmospheric pressure is as much as being 2/3 of a mile under the sea. Don't go there. Now we have See, when we look in the telescopes, we don't see all this stuff. This is an ultraviolet light. NASA put the colors in. We just see a very bright white thing. And on the 10th of June, it went between the Earth and the Sun. So it went from the evening sky into the morning sky on the 10th of June.
What was that again?
Venus was a nice skinny crescent the last part of May and the first few days of June. It was a lovely, bright crescent in the evening sky. You probably all saw it out there. And then afterward, after the 10th of June, it was in the morning sky. And by now, I don't think it's quarter by even now. But if you get up early in the morning and you have a telescope and you see that bright thing in the east, have a look at it. It might be a quarter moon by now. I'm not sure. I haven't seen it lately. But Venus is very bright, brighter than our snowfields at noon. And you need to see it if you can. Only once in a year and a half, it goes between us and the sun. And it gets to be a beautiful crescent. Now, I've had a hard time for years trying to tell people how come it's a skinny crescent like that. Because that's when it's fun to look at, you know. When it's way around the other side of the sun, it's nearly full. It's no fun to see. It's too far away, and it's right behind the sun. And who wants to look at it at noon when it's right next to the sun? It's no fun at all. It's fun when it's on our side, you see, and it gets to be a crescent. Then it's beautiful to see. And so people look at it, you see, through the telescope, and they don't understand how come you just see a crescent. And they ask me, is that the shadow of the Earth? Help! Help! Anyway, so I used to tell them, it's just that the sun is retarded. It can only shine on one side of Venus at a time. And it's not shining on our side. But more recently, I've thought of another way to tell them on Haight Street. I live near Haight Street in San Francisco, and I get the telescope out there sometimes. And so we have Venus in the crescent like that, and people were asking me how come it looks like that. And I said, if the sun were between us and Venus, it would be sunny on Haight Street. Now that they can understand. Retarded there. Go ahead. These are radar pictures of the mountains on Venus, which no one has seen and which nobody will. Go ahead. These are radar pictures. Go ahead. This is Mercury. Have another one of Mercury. This is Mercury. Now please notice, we came in from Saturn to Jupiter, then to Mars, then we jumped one, and went to Venus and Mercury. Now we're going to go back. Which one did we jump? The Earth. So we're going to go back and pick up the home planet of the Earthlings. Go ahead. Go ahead, come up more. We're going to land on the beach. You watch. We're going to land on the beach. See, there we are, right on the beach. Now, if you came in from some other planet in the spaceship and just landed any old place, the chances are you'd get your feet wet. 2/3 of our planet is covered with water. You'd have to be real careful not to get your feet wet. So I had us land on the beach. So if you want to get your feet wet, you can, but you can avoid it if you want to. And I want to give you some friendly advice. You see, our ancestors lived in the sea. The saltiness of our blood now, we think it's the saltiness of the ocean. At the time that our ancestors climbed out, so long ago, several 100 million years ago, the sea has become saltier now, so now we can't drink it. 300 or 400 million years ago, we could have probably drunk the ocean and gotten by with it, but you can't do it anymore. Anyway, so if you're in the Starship Enterprise, looking for a planet with people to talk to, you need to have a planet with a saltwater ocean. So if there are no saltwater oceans, don't go down. If there are no continents sticking out, don't go down. Mammals were invented on land. The whales and the dolphins and the seals and the sea lions and all those things were invented on land, and then they went back to the water, same as we did. Anyway, we'll get to all that. And if there are no clouds in the sky, don't go down. If there are no clouds in the sky, there will not be any astronomers to complain about the weather. That's just some friendly advice. Go ahead. Now this is our moon. You can shoot another one. Now please notice that some of these craters are all smooth. You see that? This is a crater that's all smooth, and this is the mountain around the edge. Like this is smooth, this is the mountain around the edge. Can you see that okay? This is the mountain around the edge, and this is the mountain around the edge of this one. All right. Now you have to answer to me, how come some of them are all smooth like that? Show us another one. Show us another one. See, this one isn't all smooth like that. This has a splash mountain in it. See that? These guys have splash mountains inside. Now you can go back if you will. How come some of them are all smooth like this and some of them have splash mountains in them? How come? What?
For things have changed.
Never mind that. Everything is
The
changing all the time.
temperature must have changed.
No,
Some are new, some are old.
no,
Just shadow.
no. Go ahead.
Dust?
No.
Trail?
What?
A trail on the meteorite that hit?
No. When the asteroids are big enough to go all the way through the crust down to the mantle lava is already hot enough to melt if the rocks from the top are taken off. So if the asteroid goes all the way through the crust down to the mantle, then the mantle lava is taken off. I mean, the crust is taken off and the mantle lava melts. When the mantle lava is molten, it's lighter and it comes up. That relieves the pressure underneath and that melts and comes up. And that relieves the pressure underneath and that melts and comes up. And you get this lava flood of basalt. Now you see this is much darker than these. The basalt lava is darker. Anyway, go ahead. Now these smaller ones like this, you see, this one's only 65 miles across. Well, it's not that dinky, but at any rate, it is 65 miles across. And this has splash mountains inside, 2,000 or 3,000 feet tall. Now you see all this white stuff here? What's all this? What's all this stuff?
Space dust?
No, it's glass beads. When the asteroids go into the moon, they come in about 20 or 30 miles a second. Those things that landed on Jupiter, 2 years ago, came in at 37 miles a second. How long does it take you to get from here to Nelson? How far is Nelson from here?
About 35.
About 35 miles?
A
Okay.
little longer than
Kaslo, Nelson, okay?
60.
If you go at that speed, you don't stop just because you hit some stupid mountain. You go right on through the mountain, maybe 10 miles. Now those things that landed in Jupiter, you know what they hit? Just hydrogen gas. But at 37 miles a second, it don't make no never mind what you hit to explode. Don't make no never mind what you hit. It just hit a hydrogen atmosphere. Anyway, these things go right on down into the rocks, maybe 10 miles. Then you have an explosion of vaporized stone. The vaporized stone, in the absence of an atmosphere, condenses to spherical glass beads. And the spherical glass beads shine back the sunlight toward the sun. So we see all this kind of stuff when the moon is full or nearly full. See, this is nearly full. So you hardly see any shadows in there. The next picture, you won't see any shadows. Go ahead. Now here you see the white streamers from the crater Tycho. These are 1,000 miles long. They would reach from San Francisco to Denver. They're 1,000 miles long. Now here you see these big dark areas where the asteroids have gone all the way through the crust. And then these glass beads, the young glass beads, that are not more than 1 million years old. That's young, see. Glass beads that are not more than 1 million years old shine back the sunlight toward the sun. But you see even the dust grains come in at 20 or 30 miles a second. And when the dust grains hit a rock, they make a glass line socket in the rock. Because they also go to vapor, leave a glass line socket in the rock. Now I've seen moon rock about this big. Looks almost the color of a purplish mouse. But it's all covered with these little things that look like crystals. And when you look at it carefully, they're not crystals at all. They're all these little glass line sockets where the dust grains come in. So after a long time, after about 1 million years, these nice glass beads will get spoiled by the micrometeorite pits and no longer shine like that. But 1/3 of the surface material on the moon is glass. It's all over glass beads. And when the hippies get there, they'll only need drills and string.
Is the core of the moon still molten?
No, I don't think the core of the moon is molten. Do you happen to know about that? Is the core of the moon molten? I don't know that it is. I don't think it is. But the basalt underneath the crust, if you take off the crust, it'll melt because the pressure is gone.
Oh.
But that's not the same as the core. There's lots more pressure in the core.
Okay.
Okay, fire away. These are comets, you can fire them fast. This is Comet Bennett out of the Saguaros in Arizona. The next picture also will be out of the Saguaros in Arizona. This is called Meteor Crater, Arizona, and it's nearly 3/4 of a mile across and nearly 1,000 feet deep. And this is not an earthworm. This is a 2-lane highway. Now, this was made by an asteroid a little bigger than this room, about the size of railroad boxcars, about the size of this room. And it was something like 20,000 or 50,000 years ago. And it didn't come in straight. You see, it looks as though it came in straight. They don't have to come in straight. But they come in, then you have an explosion. Don't make no never mind which way it comes in, okay? Don't make no never mind which way it comes in. The explosion spoils it. If it came in from here, the explosion spoils it. If it came in from here, the explosion spoils it. You don't see which way it came in. Same on the moon. You can't tell by looking at it which way it came in. Anyway, we have one like this in Africa, which is 9 miles deep and 30 miles wide. And the asteroid that made it, if it had landed in the middle of the Atlantic Ocean, the waves would have broken over the Appalachian Mountains. So when I was in New York, where we got those mountains nearby, I asked the kids, how would you like to surf on those waves? The waves would be 1 mile high. Well, they thought that would surely be jazzy. But I had to remind them that the speed of water waves depends on the size of the wave. And waves 1 mile high go faster than 1,000 miles an hour. And at 1,000 miles an hour, your eyeballs wash out on your cheeks. Well, go ahead. What's up next? Here are the sidewalk astronomers in Death Valley, and these are the funeral mountains. Go ahead. Here's our old 24-incher down at the Riverside Telescope Makers Conference. This is John Valley. He has a telescope. He has a comet named for him. And this man has passed away. This is Brian Rhodes' old 16-incher. Go ahead. The next one will have this thing when it's new. This is the first secretary of the sidewalk astronomer. This is Brian Rhodes. He and I made this telescope. And we had a freeway portable in 3 months, and she painted it. Anyway, so it's painted blues and purples, and it was called delphinium. You know the colors of delphinium flowers are blues and purples. And so it's called delphinium, and it's still called delphinium, and it's not painted that way anymore. Anyway, that doesn't matter. Back here you see is one of our sun telescopes. See the front cover plate? It's at 45 degrees. Okay, let's have the next picture. Here it is, in downtown Yosemite Valley. And you see the front cover plate's cut at 45 degrees. Now, the front cover plate wastes most of the light. 95% of the light is dumped out, not come in at all. 5% only comes in. The mirror is unsilvered. It wastes 96% of what it gets. Sends back 4% of that 5%. So we're down to 1 part in 500. Then that's reflected from the front plate through the welder's glass into our eyepiece. So it's safe. We let her use only about 10 millionths of the incoming beam, and that only in the green. Nothing in the infrared and nothing in the ultraviolet comes through. And it's fail-safe because if her front plate were to be broken, she would not be looking at the sun at all. She would be looking across the canyon through a welder's glass. That's known to be safe. Go ahead. Here's the same telescope at Glacier Point in Yosemite. This is our 24-incher. And when we first made that 24-incher, I told Brian Rhodes that Glacier Point in Yosemite must be the best place in this whole world for a public telescope. There's that damn hotel. But we took it up there anyway, and we found out that the hotel has just burned down. This is the hotel. This is the hotel. And this is the front driveway of the old hotel that goes around behind the rock over there. That's the front driveway. So that telescope has sat there for more than 100 nights in the course of 12 years, and the seeing conditions there are most extraordinary. Now, when we got there that first summer, and we were talking about this hotel, there was a young lady there. She says, I was in that hotel when it burned. I said, we're very happy to have met you. Anyway, let's have one more picture, and I'll show you where the store is. Down in here. Down in there and then way over here. It's 6 miles to the store, the shortest way. It's 8 miles to the store around by the waterfalls. And it's 6 miles to buy some milk and 6 miles to bring it home. And it's a real pain in the neck. By the time you get your half gallon of milk to the top, all you have is an empty carton. You drank all the milk. Anyway, it's like that. Anyway, this is the basement of the old hotel. Now this is 9,000, this is, what is it? 9,000 something feet. This is 10,000 feet here. I forget what this is. 8,800, I guess. 8,800 up there. This is 7,200 here. This is 8,800. This is 10,000 up here. And sometimes we go for a walk. Up to there. And then we have to come back home again. And that's 27 miles. And after our 27-mile hike, we have to get dinner. And then we have to give a slideshow like this. And then we have to run the telescopes till midnight. And there's this overwhelming desire to lie down on the ground. Anyway, that's how we used to do all this. Go ahead. Here we are on the first trip there. On the first trip, we offered this telescope outright to the rangers if they could house it. The next picture, Brian Rose will be on the other side of the vehicle with the mirror of the 24 standing on edge with this mountain reflected in the mirror. Go ahead. Now, when you look through that telescope, it's like having an eyeball 13 feet in diameter with the pupil of your eye open this wide. Okay, go ahead. Here we are at the Grand Canyon of the Colorado, and this telescope just went off the freeway at 55 miles an hour and crashed into a post. And Gerard was not going to even pick up the garbage. I insisted we go back and pick up the garbage, so we brought everything to the Grand Canyon, which was several miles away, and we told the rangers, you've got your choice. Either you give us some plywood and we'll rebuild it, or we're out of works. So they gave us some plywood and we rebuilt it, and here we are looking at the moon 3 days after it crashed into a post. Now you see, if your commercial telescope went off the freeway and crashed into a post, you need another one. Anyway, we rebuilt this. Now this shield was made for us by the rangers in the floor of Yosemite Valley. And the rangers at Glacier Point wanted it for their own use. So they wanted to get it away from us, and we said no, it was made for us by the rangers at the floor of the valley. So they got on the telephone and called the rangers at the floor of the valley and told them to take it away from us so they could use it. See, it's on an easel like this, so we can stick it up in front of the telescopes, and everybody knows we're part of the Park Service and we're not going to squirt ink in their eyes. And so they wanted it. And so we took it down to the floor of the valley, and they said no. They told the rangers up there, no, we made it for the sidewalk astronomers, they get it. So we've had it for years, and when we're in the national parks, we get it up and put it in front of the telescopes like that. Now, many years later, a national park ranger in a navy blue uniform showed up at my door. And he informed me that he says he has heard that we have a national park shield in the vehicle. I said, yes, that's correct. And I told him that whole story. He just roared with laughter. He says, if you don't hear from me again, it's all right. So we never heard from him again. Now that's the last picture. Now you can show two more, and then you can get them out. The next one is not a picture. That's a diffraction pattern, diffraction of rays. Now we can have some house lights. And now you can ask me some questions if you need to. Do you guys get as hot as I do in here? Yeah. Want a glass of water? Yes.
During the first part of the discussion tonight, you were speaking about electrons being stripped away and coming back and glowing in various colors and such. Could you just maybe explain that in a little more detail?
Oh, yes. When the ultraviolet light hits the atoms, it tends to knock the electrons off the outside. And it tends to knock them off with a great deal of energy, so they go beep up and off like that. Now, only the slow ones come back on. Your fast ones can't come back on. Only the slow ones come back on. So when they come back on, they give away a little bit of energy, nowhere near as much as they got when they got knocked off. Whose is this?
That's Eric's. It's going around for your donations.
Oh, that's what it's for. I'm sure. We'll have to postpone it. There must be something better to fan with. Haven't you got a piece of cardboard?
Here's one.
Actually,
Well, I'll get some fire.
I've got some stuff.
Fan with some fire.
I got some out here, John.
Oh, that's better. Oh, that's lovely, thank you. That's lovely. Who got here that wasn't here before? Give this to her. Who else? Oh, I can't get him back there. You'll have to fight for him. Oh, this is very nice. That's too heavy. This is nice.
Great.
Did I get that problem solved? The ultraviolet light knocks them off with a great deal of energy, and when they come back on, the slow ones come back on, they give only a little bit of the energy that they got when they were knocked off, and so they get too hot that way.
I see.
If they get knocked off with a lot of energy and give back only a little when they get knocked on again, or when they come back on again, then they get too much energy and they get too hot. Heat is just the speed of the molecules, you know. Heat is just the speed of the molecules. Temperature is a measure of the mean kinetic energy of the molecules. That is all. Just measures how fast they're going. Actually, it measures the kinetic energy, and the kinetic energy in a gas is the same amount on any kind of atom, whether it's a great big one or a little dinky one, no never mind. Hydrogen and helium move a lot faster, and mercury moves a lot slower, but they have the same amount of kinetic energy. The kinetic energy is the same with all the different kinds of gas molecules at the same temperature. So that's how we know what happens in the middle of the sun. We can figure out how the temperature is. We know who's in there. We know how fast they're going. You know, we're really smart. We've got a lot of information on things we can't see. We don't even know what it's like in the middle of the earth. We know more about what's happening in the middle of the sun than we do what's happening in the middle of the earth.
Those electrons that get stripped off and are gone too fast to come back on.
Yes, but slow ones can come back on.
Is that the stellar wind?
Well, I didn't talk about the stellar wind here, did I? What the stellar wind is the corona seen from a distance, okay? The particles in the corona are going every which way. But the one that you see, 93 million miles over there, came from the direction of the sun. All the ones that you see way over there, 93 million miles away, came from this side. So it looks like a wind over there. Here it's not a wind, it's the corona. The people who see it over there see the ones that went over there. And they see it as a wind going that direction. You see it as a wind going this direction. It's just a corona seen from a distance. It's only at a distance that we invent the word wind. Is that part clear? Now look, I'm here to make this stuff clear. And you're here to see that I do. And if I say it so that you can't understand it, tell me that you can't understand it and make me say it rightly. Okay? It's important that you understand these things. I'm a long ways out of home to try to make this stuff clear. What else? You know, I'm about to get on your case if you don't keep me busy.
What is that stellar wind made of?
What?
What is that stellar wind made of?
The stellar wind is made out of electrons and protons mostly, bebopping at a high speed. They simply got away from the sun. and then there's a little bit of other atomic nuclei, but it's mostly hydrogen and helium nuclei. A helium nucleus is called an alpha particle. A hydrogen nucleus is called a proton. Now you see there's a difference between chemists and physicists. Physicists call a hydrogen nucleus a proton. Chemists call it a hydrogen ion. And they only talk to each other on Sundays.
But they're the only two guys that talk about this stuff.
There's a lot of trouble, you see, in the different departments at the university because they don't all talk the same language. The educational people talk educationalese, the chemists talk chemicalese, and the physicists physicalese. What else? Yes?
Saturn, you know, you're saying that the bands are only a couple of heights of the building, 20 feet high.
Thickness, yes, very small thickness.
Yeah. What is it that allows us to see them if they're so?
What allows what?
Us to see them.
Oh, you can see right through them.
But
The sun is shining on them.
Yes.
The sun is shining on them. You can see a snowstorm for a long ways away if the sun is shining on it. If you turned off the sun, you wouldn't see them. Now, you know, the Hubble telescope has found out that the ice is vaporizing. The Hubble telescope can see the stuff coming off.
So it's ice that we're looking at?
What?
We're looking at ice in Saturn?
Yes, of course. What did you think it
Well, I
was?
have no idea. That's
It's an
why-
orbiting snowstorm. It's an orbiting snowstorm. And we're quite sure, you see, that it has not been there for 5 billion years. Because the vaporization rate is way too high. They can't last for 5 billion years. We're quite sure that Saturn had an ice moon that got too close and got smashed by the tidal effect of Saturn on the moon. Shut up. If our moon gets within 10,000 miles of the surface of the Earth, the tidal effects of the Earth will smash it and we'll have an orbiting dust storm and it'll never be dark at night. Cheer up, we don't hope it'll happen. We hope it won't happen. Anyway, it's not going that direction. The moon's not coming in.
Would that be water, ice? Saturn?
Saturn, yes, mostly water ice. There may be some other things in it too. So far as we know, it's not nice, clean, fresh water.
We're kind of skeptical about snow up
Might
here
have some
too.
other junk in it. Yeah?
I guess it's back to the rings, but now Earth will shatter into little dust particles. Why is that? Like,
What's that?
The moon, or the moon, as it comes closer to Earth, it would shatter into dust particles as.
If the moon
Saturn's
came
moon-
within 10,000 miles of the surface of the Earth, the front side would be pulled too hard compared to the back side that we would smash it into an orbiting dust storm. All the pieces would bump into each other, but the moon is made of rock. It doesn't make an orbiting snowstorm, it makes an orbiting dust storm. What?
Why wouldn't it just come right into us? You know, the gravity.
That's not so easy. Why doesn't it come in now?
Well, it's in equilibrium. That's what I
Well,
was.
never mind this equilibrium bull. Never mind that stuff. This universe does not run on equilibriums, okay? That's just the thing that the chemists like to talk about. This is not an equilibrium situation. And the moon is not in an equilibrium situation. It's trying desperately to go straight, and the Earth is trying desperately to bring it in. And it goes desperately in compromise round and round.
Yeah, and I guess I'd call that equilibrium.
No, no, don't. Don't. It's not going to stay that way.
I mean, it may not, but for our lifespan, that's, I mean, depending
Well,
on.
never mind your lifespan. No big thing. Yes.
Where do the asteroids come from?
We think that there were two small bodies, much smaller than the moon, which collided between Jupiter and Mars and left all that gravel. It's just gravel. But you see, some of that's made out of iron, nickel and iron, mostly iron with about 5% nickel, and some of it's made out of rock, and some of it's made of mixed stuff. But you see, there's no good way that we know of to separate the iron from the rock, except to have it in a big thing like the moon, something like the moon, where the iron can sink in and the rocks can float on top. Now, if the stuff in the asteroid belt was not mixed, was not separated like that, so some of them are iron and some of them are not, then you might have had some other model. But so far as I can see, there's no other model for this asteroid belt. Now, one of the astronomers, Donald Goldsmith, the one who wrote up the book for the television series, The Astronomers, Donald Goldsmith, he says that's not the modern view. So I wasn't going to hassle him in front of his audience, but I've asked several astronomers later, since then, and they all agree that's the view. That you have to have it separated by gravity, the iron going into the middle, and then bust it up in order to get what we have. But the total stuff in the asteroid belt is smaller than what we have in the moon. And I once heard a kid who had a speech defect. Did he give a whole lecture like this? Give a whole lecture like that on the asteroid belt. And he has calculated that a peanut can orbit an apple at a distance of 1 foot in the asteroid belt. I was so proud of that kid for giving a whole lecture to an audience of 300 people with a speech defect like that. Lordy, lordy, what a hero. Whew.
How long would humans live on the Earth if the moon just kind of cracked up?
If the moon collided with us?
Yeah.
We'll get to that. I suppose we could do it right now. Suppose we have the moon, instead of orbiting the Earth, suppose we have it on the top of a marble pillar over Los Angeles. There will be an armed guard at the foot of that pillar, and the dogs will not be allowed to pee there. Do you understand what the problem is? If the moon comes in free fall from a quarter of a million miles away, the moon goes to vapor and the Earth goes to gravel. Got the picture? The moon goes to vapor and the Earth goes to gravel. Now I have to ask you this question. Suppose in your mind you let the pillar get shorter and shorter and shorter and shorter. The problem gradually gets less and less. Now in your mind, let the pillar get taller and taller and taller, and the problem gets worse and worse and worse because there's more and more energy involved in it. Where is that extra energy? Is it in the moon? Is it in the Earth? Or is it in the space?
I'd say it's space.
Thank you. See how funny this thing is? Whoever thought that all that energy is in the space? Now let me tell you something about these modern spook people. They know how much, the physicists know how much energy is in this space. And these spooky people want some psychic way to milk it. I ran into that in Northern California just recently. They want to milk it by some spooky device. But you see, the way you milk it is to let the moon fall. And it comes right up. It comes right up. And there's no other way to milk it. Okay? There's no other way to milk it, in spite of it. There's no other way to milk it. I don't think I answered your question, though. Ask it again, please.
Well, just how long humans would exist on the
If the moon came down like that, about 1/100th of a second, maybe.
Oh. That was neat.
If the moon took off, then we'd also be in a different orbit.
We have to talk about tides tonight, and that's one of the things we're going to talk about right now, and let's get started. I'll get it. Suppose the Earth is over here, and the moon, no. The Earth's going to be like this. I'll see if I can draw it. It's not very good. I'm not very good at this. I think I better do it better than this. But since I have this nice gadget here, I'll see if I can pretend that I'm good at this. Let that be our Earth. Isn't that lovely? Woo-wee. And say over here we have a moon, okay? I want to know what the moon does to the Earth. Does it cause it to bulge?
Yeah.
Gravity pulls harder when we're closer?
Yeah.
All right, so the front side bulges towards the moon? Like that? Which way does this side bulge? Toward the moon?
I guess.
No.
You get to vote on this.
No.
You get to vote on this. How many think this bulges toward the moon? Put up your hands. How many think it bulges the other way? Put up your hands. It bulges the other way, you silly geese. This side is too close to the moon compared to the middle of the earth. The middle of the earth is too close to the moon compared to the water on this side. So this side also bulges. We have a high tide twice a day, not once a day. Twice a day. Now, where do you look for the moon when the tide is out? Where do you look for the moon when the tide is out?
On the horizon.
On the horizon. Is that clear, you guys? Here the tide is in, and here the tide is in, and here the tide is out. Got it? All right. Now, I was on Jim Dunbar's show on the morning of the San Fernando quake. And so we had to postpone everything because there was so much news about the San Fernando quake, because there was a lot of damage down there in the freeways. You should have seen the freeways after all the twisted metal and all these big concrete piles. Oy, oy, oy. The spaghetti piles went down. Anyway, so he asked me, isn't it a coincidence that there's going to be an eclipse of the moon, and there's an earthquake, and they're bringing the astronauts back from the moon? Well, I said, bringing the astronauts back from the moon is coincidental, and I wouldn't have done it. And I explained on the primetime TV, you see, what they would have seen. They would have seen a total eclipse of the sun by the Earth. But the Earth has an atmosphere. And they would see sunset light all the way around. I described it in the primetime TV and told the follow program where to go. Anyway, and I heard it myself afterward. They repeated it so I could hear it. And, but I said the others are not coincidental. There's a tidal effect in the Earth's atmosphere. There's a tidal effect in the water, and there's a tidal effect in the rocks. We have about a 9-inch tide in the rocks. So if it's going to go, you would expect it to go at the time that the tidal stress is at a maximum. So they repeated that on the primetime news all the time. The scientists say da-da-da-da-da. And the following year, somebody analyzed it statistically. There's a slight correlation. And then came the Jupiter effect. These two jerks came out with this notion that when the planets line up, California's going to slough off into the Pacific. Well, it didn't do it. Anyway, one of them took it back, the other one didn't. Yeah.
Was there an eclipse when I lived there then? And I only remember the freeways falling down. I don't remember that there was an eclipse.
Yeah, there was an eclipse that night, yeah.
There was?
Yeah, there was.
Didn't hear things.
I was in Golden Gate Park with the telescope.
How were the tides?
What?
Were they, are you into the ocean?
We have especially big tides, especially when the moon is closer to us than when it's not so close at all. But I don't know whether the tides were especially big at that time. I don't happen to know that. But the tides are at a maximum when the moon is full or when the moon is new. That's when the tides of the sun and the tide of the moon add up. Now you see, if the sun is, let's say, if the sun is over here or over there, if the sun's over there, the moon is new. If the sun's over here, the moon is full. Then we have maximum tides because the stretch of the Earth by the sun is added to the stretch of the Earth by the moon. Whereas if the sun is up this way or this way, then the stretch of the Earth by the sun is subtracted from the stretch of the Earth by the moon. Which is bigger, the tide due to the sun or the tide due to the moon? You get to vote on this. The sun is a lot bigger. Which tide is bigger, the tide of the moon on the Earth or the tide of the sun on the Earth? You get to vote. How many for the sun on the Earth? Please put up your hands. How many for the moon on the Earth? Please put up your hands. if the tide of the sun was bigger, the tide would always be high at noon. All right. Now, the Earth has to spin through these bulges. Where does the spin of the Earth go? Because if the Earth spins through these bulges, there's a certain amount of friction, and it slows down the spin of the Earth. Where does the spin of the Earth go? You know, the universe has rules. You can't just get rid of spin. You got to put it somewhere. You can cancel it if you like, if you have some opposite spin to cancel it with. But if you don't happen to have any, you're stuck with it. Where does the spin of the Earth go? It goes to the moon's orbit, and the moon is going away. That's why it's not coming in. The moon is going away about this much a year. Cheer up, but after a while, there are not going to be any total eclipses of the sun. So if you want to see total eclipses of the sun, get it done in this lifetime. The moon is going away. It's not coming in. It's going away. Now it's trying desperately to fall down on the Earth, and it's also trying desperately to go straight. But it's not going to be able to do either one. It has to go away a little bit because it's slowing down the spin of the Earth. Now the Earth has already stopped the spin of the moon. Now suppose we stuck around a long, long time until the moon stopped the spin of the Earth. Let's just say that by that time the moon would be far enough away so that the month would be 50 of our present day. Got it? Now you have to think. Well, let me ask you all another question first. How often does the sun rise on the moon?
About once every 28 days.
Once a month. Is that clear to you all? See, you shouldn't have told them so fast. They didn't even get any exercise.
It's my hobby.
The sun comes up once a month on the moon. So let's just suppose by the time the moon goes that much farther away, that the month is now 50 of our days instead of 30 of our days. All right. How long will a day be on the Earth? We're talking about the moon stopping the spin of the Earth with respect to the moon. How long would a day be on the Earth? What?
34.
What?
30, 40 hours.
No, it's 50 days. We're talking about the moon stopping the spin of the Earth with respect to the moon, and the month is 50 days. So the sun comes up and stays up for 25 days and nights. There are no nights. Okay? The sun comes up and stays up for 25 of our days and nights. Then it goes down and all the water freezes. When it comes up it boils, and when it goes down it freezes. Now you have to think how nice this would be, you see. And then all the hot air will run around to the cold side and sit on the ground.
Would they be spinning at all, though? Would they just be sitting still?
But what be sitting still?
Well, the moon just sits there and the Earth sits there.
No, they're going around like this with respect to the sun. They're still going around each other. We didn't do that and neither that. But we've stopped the spin of the moon with respect to the Earth, and the moon is slowing down the spin of the Earth with respect to the moon, and if it ever stopped it, then we'd have that situation. Actually, it doesn't get it stopped for about 5 billion years, and by that time the Earth will be molten anyway, and nobody will give a darn. Cheer up. Things are sure to get worse. Now you remember we talked, I think, last night, that the sun's going to swell up as a great red balloon, and it's going to puff off some of its stuff from the outside, and so because of its puffing off like that, it's going to lose some mass and won't hang on to it so hard, and we'll be about as far as Mars when the sun swells up to a great red balloon. So we will not be evaporated. I used to think that the Earth would be evaporated, but now we think that it will just be melted. The atmosphere will be long gone, the oceans will be long gone, and we'll have just molten lava. Cheer up, things are sure to get worse. All right, what else now? We talked about tides. Oh, but you notice in those galaxies, how big the tides were in the galaxies? Did you see that? That's because Well, you see, when it comes to the Earth and the Moon, they're a long ways away compared to their distances across. See? But if the Earth came way out to here, then this side would be twice as close to the Moon as the other side. Do you get it? Then it would be pulled 4 times as hard, and it would reach right out there. Got it? Well, that's how the galaxies are. The close side might be twice as close to this thing as the far side is. So this gets pulled way too hard compared to this side. And this side lags way behind, and that's how you get those spiral arms. The Earth doesn't have spiral arms due to the Moon. That's not what makes these mountains. All right. Now you have to tell me, how did the stuff in the solar system get sorted so that the planets near the sun could be made out of iron and rock, and the planets farther away?
Divine intervention.
Why do you only say iron and rock? What about gold and the rest of the elements?
That's rock. Haven't you noticed? You don't drink it. It's rock.
It can be melted. I mean, you know,
So can the rocks be melted? Don't give me
so
that
can
stuff.
iron. I don't see why you isolate iron just because it's in larger quantity.
What?
Is it larger quantity? Is that why you say iron and rocks?
Because the Earth is made out of iron in the middle, and then it's made out of basalt on top of that, and then it's made out of continents on top of that, with a little bit of water here and there. What did you think it was made out of?
Here again.
Dogs and cats?
If I knew everything, I wouldn't waste my time being here.
Well, bravo. Now you see, it would be very interesting if we knew everything except one little point. Then we could cover that one little point, and we could all go home and have ice cream. But it's not like that, you see. And in order to understand this point, you have all the reason to understand this point, and it's really a mess. But the Earth, what did you think the Earth was made out of? The middle is an iron core with 5%.
If that's what rhetoric, I'll let you carry on. But what I thought, like, there's all the elements, and then in my mind, theoretically, well, couldn't you have some planet made of gold as the center, or some other element, or does it always have to be?
Because that's not the abundance of the elements that come out of an exploding star. We're stuck with what the stars deliver. The manufacturers of these heavy elements are the stars. And they're also the deliverers of these heavy elements. And it comes about the same when one star blows up and when another star blows up. Because the chemical procedures that blow them up are about the same in the two stars. So you get about the same kind of stuff in any stellar explosion, we think. Except for some differences. Some of the stars are double stars when they explode, and some of them are single stars. Now that's a difference. If a single star collapses in the middle, it might still have hydrogen on the outside, and when it blows, all the hydrogen is there. That's type 2. Now type 1 is a double star, like Sirius. Sirius A, right now. Do you understand Sirius? It has a companion star with a density of 60,000 pounds in a 1-pint jar, called a white dwarf. 60,000 pounds in a 1-pint jar, and it's going around Sirius A. Sirius A is a very bright. Sirius A is a very bright star, and this other thing is very dim. But we knew it was going around, and Alvin Clark noticed it when he was trying to read his telescope, a 19-inch lens telescope. He was trying to read it on the bright star Sirius, and he sees his companion. That's how it was actually discovered. Anyway, we know quite a bit about it now, and we also know that it used to be the bright star. And it swelled up to a great red balloon and transferred its stuff onto its little companion. And its little companion is now Sirius A. And what's left of the old bright star is this dwarf star that was in the middle. So now the big bright star is Sirius A. Now it's going to swell up to a great red balloon. Cheer up! It'll swell up to a great red balloon and transfer the stuff back. Now you've got to think what's going to happen when all this hydrogen lands on the star with a density of 60,000 pounds in a 1-pint jar. It's not like landing a here. So it piles up on the surface, maybe 3 feet deep, and bowie, off it goes. And after another 100 years, it does it again.
100 years?
Yeah, something like that. Most of us don't live long enough to see these things go off over and over again like this. But at any rate, they go off over and over like this, and that's called a recurrent nova, and it's one star eating another one. Okay? Now, if the Sirius B were to add enough stuff, I mean Sirius A was to swell up to a great red balloon, and dump enough stuff onto Sirius B so that it weighs more than 1.5 times as much as the sun, then it goes supernova without any hydrogen on the top side. That's type 1. The astronomers name these things before they know what the hell is going on. That's type 1, supernova. Type 2 is an ordinary star with all the hydrogen on the outside. So we have different things, you see. But when the star collapses like that in the center, the stuff, all these heavy elements come out about the same, whether you have hydrogen on the outside or you now don't have hydrogen on the outside. What happens inside is pretty much the same. But there is a difference on the outside, whether you have hydrogen and helium or not. Wow, we don't usually cover all that stuff. All right, now you have to do the homework.
So our son ended up.
Yes?
Just as a little information, if Sirius were to do a type 2,
Would we survive? I don't think so.
that's what I was,
I don't think so, no, I don't think so. The Crab Nebula star is 6,000 light years away, and Sirius is 8.5 light years away. There's a gross difference in distance. And the brightness goes as the square, you know, the brightness falls off as the square of the distance. And I'm not at all sure that life would survive on Earth if Sirius B goes supernova. I've thought about it a lot of times, but I'm told that probably Sirius B is not massive enough to go supernova even after Sirius A transfers its stuff to its surface. Anyway, it'll be several weekends, don't worry about it.
It's not a problem.
What?
It would fill up that large a slot around the space with heavy radiation.
Yes, it might be quite gross, yeah.
Were the supernovas we have seen, where were they? How far away were they?
The one we had in '87 was in the Large Magellanic Cloud. That's in somebody else's Milky Way, not in our own Milky Way. Now, Tycho saw one. Tycho was on his honeymoon, and he saw a supernova, canceled the damn honeymoon, and went home to the observatory. And Kepler saw one, and Richard Feynman says, now I have mine. What else?
What's Feynman's supernova?
The one in the Magellanic Cloud.
Oh, he's on
All right, now you have to explain to me. The Earth really is made of iron and rock. And you have to explain to me how come the planets near the sun are made of iron and rock, and the planets farther out are made of hydrogen and helium. You can try. You're just as good at guessing as these jerks are. You watch how bad they do. You can try. How come you think that the planets near the sun would be made out of iron and rock, and the planets farther away would not be made out of iron and rock? How come you think it would be like that?
Would the sun pull the rocks in?
What?
Would the sun, the gravitational of the sun pull the rocks in?
No, gravity pulls everything evenly. Doesn't make any difference whether it's hydrogen or rock. It doesn't care about things like that. Yes.
That's sort of what I was going to say.
Oh, both of you. Okay, let's have a better effort. Now let me tell you something. Don't be embarrassed if I jump. Don't be embarrassed if I make fun of you. It's just for the fun of it. It's just for the fun of it. Don't be embarrassed. I don't care how wrong you are. The wronger you are, the wronger you are, the more clear it is to the class that that's wrong. Don't you see? I don't want you to come up with the right answer. That's why I jump on him. He's been through this before, 2 years ago. I should have put a gag on him with cotton in his mouth. However, he's been very polite today. But you do understand, I have to have you people work your heads. If you don't work your heads, so that if there's a problem in your mind that's going to be answered by somebody in the class, then you won't hang on to it. You hang on to the information when it's important to you. When a woman becomes pregnant, she studies childcare. We don't study it. We don't give a damn.
Well, could part of it be the spin, just how fast they're spinning?
All right, keep going. What can you do with this bit?
Well, things expand. If you're spinning and it loses a bit, the gas or whatever.
Yes, but the spin would throw all the iron out just the same as it would throw the hydrogen out.
Well, let's say you're not spinning too fast.
No, you can't have it spin for one of them and not spin for the other.
Well, let's say we're all spinning, but the faster you go, just as you were talking, what was it, one small star was spinning at how many times per
We think the sun used to spin 200 times faster than it spins now. The question is, how did it get the material sorted so that planets near it could be made out of iron and rock, and the planets farther away could be made out of hydrogen and helium?
Certain elements lighter, they get flung off first, and heavier stuff later.
Why?
Well, because of this.
There's no good reason for that. The spin doesn't do that.
Math.
No, gravity treats them all evenly. Gravity treats them all evenly. You see, I went to the university under Lawrence, and the inventor of the cyclotron, and he had evacuated tube. And he had a feather in there and a penny, and he picked it up like this, and they both hit there, and then they both hit there, okay? Don't mean no, never mind. Gravity is very broad-minded. It handles everything the same way. So you can't do it that way. Yeah.
Would it be because their spin isn't as large?
Yes, but why would the spin throw the light stuff away and not the heavy stuff?
Well, it would be like you said earlier.
Anyway, it wouldn't. So don't push it. Yes.
And that little toy you were playing with last night at Eric and Maryland's, you know that water thing?
Yeah.
The sands of similar color collect. Okay?
That has to do with the density of the sand.
Well, different atoms have different densities.
It's not in vacuum.
Yes, but this is not a floating problem.
Yes, it is.
No, it's not a floating problem.
Yes,
The
it is.
planets are not floating. No,
Yes.
it is not.
They're floating.
It has no, they are not floating. Floating means you're riding on something with a bigger density.
Space has a bigger density.
No!
Yes.
Don't be such a smartass.
Well, this is stuff.
No, it's not a fact, and you can see it perfectly well that it's not a fact, and you're just showing off.
Well, things float.
No, planets are not floating.
It's a vacuum. Evacuated too. It's the penny and.
It has nothing to do with floating. Nothing whatsoever to do with floating.
Well, that's.
They're orbiting the sun. They're not floating on anything. A ship will float on this lake because the ship is lighter. That's the only reason it floats.
Well, an atom is on top of space.
No, it's not.
Okay, well, space makes way for an atom.
The way is the space.
The what?
Space doesn't make way for something. What you call the way is space.
Well, if something displaces space, then it exists.
Space is not an oozy thing like toothpaste.
Right.
It's not.
I know that.
And nothing floats on it. You'd have a lot better chance of floating if you jumped off this roof than you would outside of the Earth's atmosphere. If you come in from outside of the Earth's atmosphere, you'd land at 170 miles an hour.
Well, the point that I was trying to make, though, is that with that vehicle for studying the way things that are alike attract. And that's what
Electrical things that are alike do not attract.
But some things do. Electrical is not the same
Yes,
as
people do.
gravitational or magnetic.
What? Anyway, that has nothing to do with the problem at hand. It doesn't sort the stuff in the solar system.
Well, I give it my kick of the cat. I give up.
What about the process in the sun itself? Like,
What about what?
the process, like nuclear fusion, what's taking place in the sun? Could certain things happen first, like in a sequence? And then
No. The sun is only making helium out of hydrogen. And that has nothing to do with the sorting of the material in the solar system. Come on, can't you do better than that?
Did the sun? Are you going to tell us what order the planets were created in? Or does that make any difference?
Well, it might make some difference, but I don't know. I wasn't sticking around that long.
Did the sun do the sorting? Is that
Yes.
what you're saying? The sun did the sorting.
I'll give you 10 points for that. The sun did the sorting. How did the sun do it?
Because
What?
of the heat of the sun?
What?
Is it because of the heat of the sun?
All right, I'll give you 10 points for the heat of the sun. What does the heat of the sun do?
Burns things.
What?
Burns things.
No, it doesn't.
Solar wind.
It floats.
Solar wind, I'll give you another 10 points for the solar wind. Nobody's got 90 points yet.
Different things condense at different temperatures.
That's true. Different things condense at different temperature. I'll give you another 5 points for that. What is the main thing?
Movement.
Movement has something to do with it. I'll give you a point for it. What direction are things moving?
Outward?
Not outward.
In.
Yes, you can talk in this class with your hand. Thank you. You get 10 points for this.
Revolving around.
They're not going outward. They're going this way.
They're going out, they went out from the sun, is what
No, not necessarily.
Well, the solar wind can push a hydrogen atom, but it can't push something heavy.
Did you hear what he said? However, that's not the main thing that does it. The main thing it does it is the great magnetic egg beater. When the sun was spinning, its whole magnetic field has to spin with it. Now, what kind of things are pushed by a magnetic field? What?
Charged particles.
Charged particles. Iron is not pushed by a magnetic field, and magnets are not pushed by a magnetic field. If you drop a magnet, it doesn't go bebopping off to the north. You probably noticed. They fall straight toward the center of the earth. But electrical particles are moved around in a magnetic field. Now, why are the particles electrical?
Energy?
Because of the sun's radiation. That's what made them hot. The sun's radiation knocks the electrons off. The ultraviolet light from the sun knocks the electrons off, and then there are electrical particles, and then the magnetic field pushes them away. All right. Now, how many electrons do you suppose the sun knocks off? 26 from iron or 1 from iron?
1?
1. You get 90 points for that. 1 from iron, and how much from hydrogen? 1. Now, if you had to push a Mack truck loaded or a bicycle without a passenger on it, which one's easier? A hydrogen atom has a weight of just 1, and iron nearly 50 times that heavy. And the amount of push is the same on the iron as it is on the hydrogen. And the hydrogen goes scooting out there, and the iron does no such thing. Now is it clear? It takes about the same amount of energy for the ultraviolet light to knock an electron off of iron or off of hydrogen. The ionization energy is about the same, about 13 electron volts. But that's not what the difference is. The difference is that there's only 1 push on each of those atoms, and the iron atom is heavy and hard to push, and the hydrogen atom is not heavy and hard to push. And so the great magnetic egg beater can speed up all this light stuff and push it on out there, and the heavy stuff is left behind. It's the great magnetic egg beater that does it. That's my language, the great magnetic egg beater. But you have to think of the magnetic field of the sun like a great wire egg beater, and when the sun goes around, the egg beater goes around. Now, what happens to the egg beater if it speeds up the eggs. What happens to the egg beater if the eggs speed up? What happens to the speed of the egg beater? Slows down. The egg beater slows down and transfers its spin to the eggs. That's why the sun spins so slowly. Once in a month it goes around. And it used to go, we think, 200 times in a month, several times in a day. But the egg beater transferred its spin to the stuff that it pushed away. And most of it pushed way, way, not in our solar system anymore at all. Most of the stuff got pushed way out to the hovering layer again and flattens again into the disk for the newer stars. Got the picture? Now, there's another problem. If you think, let this be the sun this time, and we'll erase the galaxy. Let this be the sun, and the heavy stuff, we'll say, will form a kind of a distribution in here. Littler amounts out there and bigger amounts in here. And so we're going to have Venus in here, and the Earth in here, and Mars out here, and Mercury in here, okay? Just the way you'd expect it. Just the way you'd expect it. Now, why don't we have the same thing with the lighter weight material, Jupiter and Saturn in here, and lighter weight stuff on the ends? We don't. We have the biggest one in here because Jupiter and Saturn are stars. Jupiter and Saturn are not planets, they're stars. They spin way too fast to be planets. The planets in our solar system were made when the sun was slowing itself down. It pushed all that stuff away, and it slowed itself down, and all the planets are spinning slowly. And Jupiter and Saturn are spinning like hell. Jupiter is big enough to put 1,300 Earths inside of it, and it spins around in less than half a day. Now we know where we are in the galaxy,